A very warm good morning to respected dignitaries, Principal Dr. Venkatesh Sir, Managing Director G. Raghunath Reddy Sir, Correspondent Srimati V.K. Padmavatama Madam, Director Srimati V.K. Srivani Madam, Resource Person, Convener, Co-Conveners of the program, and all the participants of the FDP. Behalf of Gates Institute of Technology and the Department of Humanities and Basic Sciences, I, English, would like to extend a warm and a hearty welcome to each one of you for this 1 week international FDP on mathematics for a better world. I thank you all for being here on this virtual platform. The world is full of diamonds and gems, and we are having some of them here to build this event. With this note, I would like to welcome our guest of honor and resource person of the program, Professor E. Keshava Reddy Sir, Department of Mathematics, Director of Evaluation, JNTUA, who is expertise in this area, and for accepting your request to share this knowledge with all of us. I welcome our chief guest of today's program, Professor R. Bhona Vijaya Madam, HOD of Department of Mathematics, JNTUA. I welcome our legendary Managing Director, Sir, lovable Correspondent Madam, our Director Madam, and beloved Principal, Dr. D. Venkatesh Sir. I thank them all giving their valuable time for us. I would like to thank you all for taking the time out from your heavy schedules and making this a spectacular morning with your glorious presence on this virtual platform. Without taking much of your precious time, I'll begin the program. So now, I welcome our dedicated and ambitious HOD of H&S department and also convener of this FDP, Dr. G. Haripriya ma'am, to address the participants.
Distinguished keynote speakers from premier institutions, delegates, colleagues, ladies and gentlemen, good morning. On behalf of Department of Humanities and Basic Sciences, Gates Institute of Technology, I'm delighted to welcome you this morning to 1 week faculty development program on mathematics for a better world. Thank you for being here on this virtual platform and to bring your energy, ideas, and expertise. We have 350 participants from the different parts of the country and abroad. I would like to welcome and give special thanks to our Managing Director, Sri G. Raghunath Reddy Garu, our correspondent, Srimati V.K. Padmavatama Garu, our director, Srimati V.K. Srivani Garu, and our beloved principal, Professor Venkatesh Garu, for their suggestions and support, and my team who have been supported me throughout this program right from its inception. And I welcome and thank today's chief guest, my guide, eminent personality, Professor R. Bhona Vijaya Garu, Department of Mathematics, JNTUA, College of Engineering, and coordinator of Women Empowerment Cell, Nantapu, for giving her valuable times for us in spite of her busy schedule. Gates Institute of Technology was established in 2001, is permanently affiliated to JNTUA and accredited by NAC. The institution also got recognition of 2F and 12B from UGC. Institution is certified by ISO. The focus is to inculcate continuous learning habit with positive attitude and ethically sound values within the faculty and students. The institute has always envisioned instilling life skills among the students through their participation in various curricular, extracurricular, and co-curricular activities. Progressive thinking of our late correspondent Sri V.K. Reddy Garu has made Gates stand tall as one of the very fast and few educational institutions to completely run on solar power. I extend my heartfelt thanks to Professor E. Keshava Reddy Garu, Department of Mathematics, Director of Evaluation, resource person of today's session, Differential Geometry for Machine Learning. The institution is headed by Dynamic Managing Director Sri G. Raghunath Reddy Garu, Correspondent Srimati V.K. Padmavatama Garu, who is the heart and soul of our institution, and Director Srimati V.K. Srivani Garu, who is giving a new directions to the institute. The department has well qualified, dedicated, and experienced faculty and committed support. The institute allows students to further enhance, update, and fine-tune much needed specific domain skills and soft skills through various training programs and workshops at different levels. In order to facilitate this, the institute signed an MOU with Village Energy Australia, APSSDC, IUCEE, Florida Atlantic University, USA. The main objective of this FDP is to ensure that the faculty members enrolled in teaching the courses like machine learning, discrete mathematics, and cryptography shorten the skills further, build a network with other peers, and get exposed for the advances in the field of mathematics, especially the applied domain. The purpose of this FDP is create awareness and also prepare the faculty members and make them acquire necessary expertise in these areas. Thank you. Thank you very much for giving your valuable insight on FDP.
Thanks a lot for your precious words, ma'am. It gives me immense pleasure to welcome our beloved principal, sir, Dr. D. Venkatesh, sir. I request you, sir, please address our participants, sir.
Yeah, thank you very much, ma'am. Chief guest of today's function, Professor R. Bhuvana Vijaya, Madam, Professor and Head, Department of Mathematics, JNTUA College of Engineering, Anantapuram. Guest of honor, Professor E. Keshava Reddy, sir, Professor and Director of Evaluation, JNTUA University. Respected correspondent of the institution, Srimati V.K. Padmavati, Madam. Our young and dynamic managing director, Sri G. Raghunath Reddy, sir. Honorable Director of the institution, Srimati V.K. Srivani, Madam. HOD, Dr. G. Haripriya, Madam. Coordinator, Dr. G. Shanti, Madam. Other faculty members and participants. Good morning and a warm welcome to the 1 week faculty development program organized by Department of Humanities and Basic Sciences. At the outset, my sincere thanks to all the managements and the principals for deputing the faculty for this faculty development program. The main motto of this faculty development program is to share and interact with the advanced technologies that are present in the mathematics nowadays. In our daily life, mathematics plays a key role. Usually, the engineering students will be thinking that there is no use of mathematics in higher education, which is a misconception. Without the mathematics, nothing is there. That is, it is a big zero. Again, here we are using the zero, that is a mathematics. That is the importance of mathematics in engineering. And this mathematics is playing a key role in cryptography, network security concepts also. So that's why we appeal to all the faculty community actively involve and interact with the resource persons, exchange your thoughts, clear your doubts, and share the same thing with your students and motivate them to clear the subjects and actively involve in higher education and their respective fields. My hearty congratulations to Department of Humanities and Basic Sciences for coming forward to conduct such a beautiful program. Thank you everyone for giving me this opportunity. Thank you very much.
Thank you so much for your words of wisdom, sir. Now, I would like to take the privilege to welcome the backbone of our college, our lovable correspondent, ma'am, Srimati V.K. Padmavatam Garu, to please address the participants.
Good morning to everybody. This is V.K. Padmavati, correspondent of Gates Institute of Technology, Gutti. Good morning to everyone once again. It gives me immense pleasure to see the teaching faculty being connected through this platform. I congratulate Department of H&BS of Gates Institute of Technology to innovate this activity, a one-week online faculty. Connected platform. This activity, okay. A 1 week starter. Okay. 1 week online faculty development program on mathematics for a better world. I thank Professor Bhuvan Vijay Garu, HOD, Department of Mathematics and Coordinator of Women Empowerment Cell from JNTUA as a chief guest. Why it is online faculty development.
HOD of Department of Mathematics, Coordinator of Women Empowerment Cell from JNTUA as a chief guest, accepting this invitation on this inaugural session and motivating the participants for this program. I thank Prof.E.Keshava Reddy Garu, Director of Evaluation, for accepting our invitation as a guest of honor and for addressing the participants. I also thank all the eminent speakers and for accepting the invitation to share their knowledge. This kind of platform provides educators, faculty, and research scholars to improve the quality of education and imparting the same to the next generation. I wish all the participants will make the best use of it and equip themselves to provide good research and quality education. And I wish all the best for all the participants. Thank you, all of you, sirs.
Thank you so much for your kind words, ma'am. Now, I request our energetic director, Srimati V.K. Srivani ma'am, to share a few words on this occasion.
Good morning, one and all. I thank distinguished dignitaries Bhuvan Vijay Madam and Dr. Keshava Reddy sir for accepting our invitation and taking a part of this FTP on mathematics for a better world. The title looks very apt because mathematics is needed for this modern day advancements, where whatever we talk, be it be computer science or be it be marine biology, whatever we talk, we need everyone to have an understanding of basic mathematics. Then only the world can move forward. So mathematics is definitely needed for the better world. And today I congratulate and thank each and every one of you who have registered for this event, and who are attempting to improve your skills and knowledge in the mathematics. Though you have been teachers, I know all of you are well versed and good teachers, but whenever you get a chance, learning is a continuous process, and taking part in the faculty development programs like this, it will polish your skills, let you learn new technologies and new concepts. And also as teachers, maybe get an opportunity to share the best practices as teachers to benefit your students, to learn new best practices. So having said this, we at Gates Institute of Technology always encourage these kind of activities, and we encourage our faculty to conduct this kind of development programs, and also encourage our students to take part in many such other activities, which not just academically improve them, but even the co-curricular and extracurricular activities, which are really the life, which really teach them the life skills. And I know today it has been a little delayed event, and I don't want to take much time. And once again, I thank Bhuvana Vijay Madam and Keshava Reddy Sir for accepting our invitation for today's event. And I thank and wish all the participants best to get best out of this event, and best wishes to all of you. Thank you. And I appreciate our H&S department, Humanities and Basic Sciences department, to come forward with an idea to conduct this FDP and taking an active part, and particularly our HOD Haripriya and all the faculty who have taken active part in this. I appreciate your initiative, and I wish you all the best. Thank you.
Thank you so much for your valuable words, ma'am. The empowered woman is powerful beyond measure and beautiful beyond imagination. I'm happy to introduce the chief guest of this FDP, Professor R. Bhuvana Vijaya Garu, MSc, MPhil, PhD, Associate Professor, Department of Mathematics, JNTUA, College of Engineering, Anantapuram. She completed her graduation in BSc in SK University, Anantapur. Later on, ma'am pursued MSc, MPhil, and PhD from SK University, Anantapur. She has over 22 years of teaching experience, an assistant, associate, and a professor at JNTUA College of Engineering. She has done around 55 publications from 2001 to 2017. She has attended over 21 conferences and seminars. Ma'am has guided 8 PhD studies on our Haripriya Madam is one among them. We all feel elated for having ma'am as a chief guest of today's program. I take immense pleasure to welcome you, ma'am, and I request you to speak a few words on this event. Good morning, ma'am.
Good morning, ma'am. Thank you. Thank you, Vijayalakshmi, for introducing me. So, respected Principal, Professor Venkatesh Garu, Gates College of Engineering, today's guest of honor, Professor Keshava Reddy Garu, and correspondent of the Institute, V.K. Padmavati Garu, Managing Director of Gates Institute of Technology, Sri Raghunath Reddy Garu, Director, Srimati V.K. Srivani Garu, resource persons of this FDP, Professor Radhakrishnamacharya Sir, Professor D. Srinivasacharya Sir, and Professor Keshava Reddy, Shaila Kumari, Dr. Shaila Kumari, and Dr. Maheshwar Rao. Convener of this program, Dr. Haripriya, co-conveners and participants of this program, a warm good morning to all. I'm delighted that the Department of Humanities and Basic Sciences of Gates Institute of Technology will be organizing 1-week faculty development program on mathematics for better world. I appreciate the intellectual zeal and the wholehearted endeavors of the organizers in providing such a platform for faculty and researchers to deliberate on the latest advances in the field of mathematics. And I hope this type of FDPs would pave a path to improve the knowledge in applications of mathematics in various fields. So in present scenario, mathematics occupies a vital role in the development of various applications characterized by technology and other scientific developments. So in past, we use mathematics is only to get solutions of the equations, and we done research in mathematics, and they were not concentrated much on applications. Now, the research in mathematics has multidisciplinary in nature with a significant potential to fabricate new functional devices for wide range of applications like artificial intelligence, machine learning, 3D printing, biomedical equipments like heart lung pumps, peristaltic pumps, etc. So we have so many applications in biomedical field and also in the computer science, IT sector and all. So in COVID pandemic situation, the role of mathematics is not ignorable because, for example, in IIT Kanpur developed a mathematical model which is used to predict the number of COVID cases or more in which month. So in which month they are more, in which month they are less, etc. So by using this data, the government of India took precautionary steps to reduce the number of death cases. So also in new education policy, Government of India concentrates on multidisciplinary mathematical courses. In future, mathematical subjects occupies very important role in the development of science and technology. So in the place of traditional mathematical courses, interdisciplinary mathematical courses will come. So in government universities, we have some limitations to introduce new mathematical courses, but there is a chance for the deemed universities and the private colleges like you to introduce new multidisciplinary mathematical courses and lab sessions like mathematics for machine learning, artificial intelligence, MATLAB sessions, R programming, etc. I hope Raghunath Reddy sir, the managing director of this institute, may come forward to introduce such courses in this institute so that Gates Institute will be the trendsetter. I also hope this FDP will enrich your knowledge and gives an idea about new technology used in mathematics in present world. I advise the participants to interact with the senior resource persons to get innovative ideas for research. So with these, I'm concluding and thank you. I thank the organizers and the management for giving me this wonderful opportunity. Thank you, one and all.
Thank you so much for your valuable words, ma'am.
Okay, ma'am.
I hope you will have a stimulating and productive program over the next few hours. I would also like to appreciate the questions for forth after the completion of this session in the chat box, and hence all the questions shall be answered. I will conclude my address with an additional call to all of you for active participation during the session. Now it's time to introduce today's speaker. It gives me immense pleasure to introduce today's speaker, guest of honor, and a resource person. He is none other than Professor Keshava Reddy Garu, Department of Mathematics and Director of Evaluation of JNTUA. He is an enthusiastic mathematician with ideologistic brain in all the fields of engineering and mathematics. Started a career as a lecturer of mathematics and now working as a professor of mathematics, JNTUA College of Engineering, Anantapur, and Director of Evaluation, JNTUA, Anantapur. After crossing different hurdles in life, he published more than 90 papers in both reputed national and international journals. He has own modular, object-oriented, dynamic learning environment site through which he teaches mathematics to BTech and MTech students online. He is also guiding research scholars by considering new challenges in mathematics. Sir has written books on mathematics which will not only improve the knowledge of future engineering students, they also help students to improve their research capabilities in mathematics. He has received Andhra Pradesh State Best Teacher Award for the year 2017 on 5th September, conferred by Honorable Ex-Chief Minister of Andhra Pradesh, Shri Nara Chandrababu Naidu Garu. He has received Andhra Pradesh State Scientist Award for the year 2020 on 22nd March 2021, conferred by Honorable Minister for Energy, Environment, Forest, Science and Technology, Shri Balineni Srinivas Reddy, Government of Andhra Pradesh. Sir's professional membership include professional members of IEEE, life member of Society for Development of Statistics, Indian Society of Technical Education, Andhra Pradesh Society for Mathematics Sciences, Indian Mathematical Society, Ramanujan Mathematical Society, and so on. Sir's research publications include 8 national journals and 76 international journals. Sir is a governing body member of SSK Institute of Business Management, Chedalwada Venkata Subbaya College of Engineering, Jagans College of Engineering and Technology, Sri Padmavati Engineering College, Ravindra College of Engineering for Women, MGR Institute of Business Management. Coming to Sir's research and consultancy, Sir has supervised 13 PhD scholars and co-supervised 7 scholars. Honors received by Sir are Andhra Pradesh Scientist Award for the year 2020 for the contribution and achievement in the field of mathematics and 22nd March 2021. National Integration Award of Andhra Pradesh and Telangana State sponsored by Healthcare International on 26th January 2018. ISTE Award of Andhra Pradesh and Telangana State Best Engineering Teacher, late Sri Jasi Sri Krishnamurthy Garu Award, sponsored by VNR Vijnana Jyoti Institute of Engineering and Technology, Hyderabad, on 29th December 2017, and many more. Sir is an author of 6 books. He has given numerous guest lectures and technical talks. I welcome Professor Keshava Reddy, sir, to address the participants as a guest of honor and take over the session and give an insight of the topic. Thank you, sir, for your accepting our request to share your knowledge with us. Please carry on, sir.
Thank you very much for introducing me. And I think it's time is already going on. The participants is waiting for the lectures, what the FDP is going on. So dignitaries, today's dignitaries, chief guest, management, and all the people. Good morning to all of you. So it's very good to see that GATES College of Engineering is having a 1-week FDP. It's good for the faculties and research scholars and the students, those who are interested in this field. So I congratulate the management of GATES College of Engineering and the principal and staff of the college, including Department of Mathematics, for conducting this one. Thank you very much for giving me this opportunity. So the lecture can, when the lecture will start, please?
Okay, sir, you carry on, sir.
So, shall I start the lecture now?
Start, sir. Please start, sir.
So I will share my screen.
Okay, sir.
So here, host disabled participation screen sharing. Please permit us. Hello.
Sir, You are audible, sir.
Yeah. No, actually the host is disabled the participant screen share. If you permit, then only we can.
1 minute, sir. 1 minute, sir. Sir?
Yeah, please. I will share my screen now.
Now you share, sir.
Yeah. So it's visible. Please check it. My screen is visible.
Yes, sir. Visible, sir.
Yeah. So, good morning to all of you. So today we are going to see differential geometry for machine learning. The topic is what the FDP has been put it, that mathematics for better world. So now these days, when you see the world is going towards everything automation, and everything is going to be make it easy. So, or in other words, you say making a people lethargic than the previous world. So when you want these all things, the mathematics part should be strong in the engineering and science and technology part. So this differential geometry for machine learning, the previously when we have what you say in PG course and UG course differential geometry, at that time we have studied about on pen and paper, and we have studied the theorems,
Sir,
what is
excuse
going
me,
on.
sir.
Yeah,
Sir,
please.
Can I interrupt, sir? Please, sir.
Yeah, please.
Sir, slides, please share full screen, sir.
Yeah, it's
These
a
are
full
your
screen.
slides.
It's full screen.
No, sir,
Slideshow.
slideshow is visible, sir.
No. This is okay. Wait, just a minute. I will go for... Now.
Yes, sir. Okay, sir.
It's okay now.
Okay, sir.
Okay. So when we go for differential geometry, so now these days when the machine comes in a picture, when the machine learning comes in picture, the differential geometry again take a very beautiful turn in making effect in the engineering and technology part. So when we see the differential geometry part, what we are going to see that is differential. So three parts: curvature of curve, curvature of surface, application of curvature. Curvature of curve. So I think all of you know about the curvature of curve. The curvature of curve, intuitively, the curvature is the amount by which a curve deviates from being a straight line. So what is curvature? How we are going to see the curvature of a curve? Intuitively, the curvature is the amount by which a curve deviates from being a straight line, or a surface deviates from being a plane. So surface deviates from being a plane, or curve deviates from being a straight line. These two we are going to say a curvature. And for curves, the canonical example is that of a circle which has a curvature equal to the reciprocal of its radius. Please mute yourself. Please mute yourself. Hello. Yeah. So now for curves, the canonical example is that of a circle which has a curvature equal to the reciprocal of its radius. So curvature is directly proportional to 1 by r, which is known as radius. Now, the example, this is one example I am speaking about, the curvature equal to the reciprocal of its radius. Smaller circle bends more sharply. If you see the smaller circles bend more sharply and hence have higher curvature. So the curvature of a curve I have taken, I am speaking about, to simple understanding, the circle curvature. So for curves, the canonical example is that of a circle which has a curvature equal to the reciprocal of its radius. Smaller circles bend more sharply and hence have higher curvature. Next is curvature of surface. So the Gaussian, generally when we speak about the curvature of surface, the Gaussian curvature of a surface at a point is defined as the product of two principal normal curvatures. What is that? The Gaussian curvature. When we speak about the curvature of surface, generally we take it a Gaussian curvature. Gaussian curvature of a surface at a point is defined as the product of the two principal normal curvatures. It is said to be positive if principal normal curvatures is the same direction, in the same direction, and negative if they curve in opposite direction. So when we are going to say positive, when we are going to say negative, the curvature, Gaussian curvature of a surface at a point is defined as the product of two normal curvatures. It means when we speak about the curvature of surface, we are going to speak that two normal, principal normal curvatures, the two principal normal curvatures products is there. It defines the curvature of surface. It is said to be positive if principal normal curvature curve is the same direction, and negative if they curve in opposite direction. This is about curvature of surface. Application of curvature, when we see, the curvature is of utmost significance in designing road curves and grinding work pieces. When we see the roads are going on developing, and when some work pieces in the corner side it is going on, at that time this curvature plays a very important role. While designing road curves, its influence on road safety needs to be considered. In order to improve the efficiency without excessive wear, its influence on the size of grinding wheel requires to be considered. So it totally depends on what? It totally depends on the thing, what we are going to say, that efficiency without excessive wear, it influence on the size of grinding wheel required to be considered. So this application of curvature is very important when we see today in roads and transport, when we are going to see the curves on the roads, and when we are going to make a highways on the road curve, designing road curves particularly. Now, so suppose now parameterization of curve. So my screen is visible now. Slides are moving. Hello. My slides are moving. Whether it is visible. Hello. Hello.
Sir, yes, sir, visible, sir. It's moving.
Slides are, yeah, fine. Parameterization of curve. So what do you mean by the parameterization of curve? When we say parameterization of curve, this is something like this. So when we say parameterization of curve, I will show you that parameterization of curve. Yeah. So when we say parameterization of curve, a parameterization of a curve is a map where we are going to see from a parameter interval to the plane. From a parameter interval to the plane. The functions xt, wait, I will stop sharing. I will put it the total, share my total. So my screen is shared. Now it is visible. Please tell me.
Yes, sir, it is visible, sir.
Visible. Wait, when I say it is not having like this. Wait just a minute.
Okay, sir.
Stop sharing and I will start. Just a minute.
Okay, sir.
Okay, so my screen is visible now. Screen is visible now.
Visible, sir.
Visible. Just a minute, because it's wait. So when my first slide will be on the screen, you please tell me, and then I will go ahead.
Okay, sir.
Our total screen is now, yeah, it's okay, visible?
Yes, sir. Visible, sir. The first slide.
Yeah, please. Yeah, now it's okay.
Okay, sir.
Okay, fine. So parameterization of curve. A parameterization of a curve is a map from a parameter interval R to the plane. Parameter interval R to the plane. The functions xt and yt are called xt, yt or xs, ys are called coordinate functions. The image of parameterization is called a parameterized curve in the plane. So now you see here parameterization of a curve. So arc length is S. So As we are going to say about xs, ys. Now see the tangent of a curve at this point is the derivative of A, that is A dash S. When I want a tangent at that point, it means I have to differentiate both x and y, that is x dash and y dash. And this is the shape when we are going to say A dash S dot delta S. So AS and AS plus delta S. That is the curve. If you see the colored link, this one, this you can see that how it is going on. This is the arc, what we are going to say A dash S and dot delta S. So this beauty plays a very important role in our machine learning part. And curvature of a curve, when we say it is A double dash S, A double dash S, we say X double dash, Y double dash, and this A double dash S is known as curvature. And we are going to show the curvature like this, that is A dash S plus delta S, A dash S, and this is the total part. So when we say parameterization of a curve, we are going to see how it is going to be parameterized and how it is going to be, how we are going to make a parametric, to convert into parametric form. So this is of a form when we are going to change it, one form, that is Cartesian to parametric form. So here, the first thing what we are going to do, we are going to parameterization of a curve, we are going to change it into the parametric form, and then we are going to define a curvature at the curve. Okay. Now, see A double dash S dot delta S. Now this shape, if you see this one, that is this. This is A dash S plus delta S. This is A dash S. This is the two vectors are here, and this is A double dash S dot delta S. This you are going to see. This part is the curvature part. When we are going to see this one, this is makes a beauty in the machine learning. And the machine, whenever we need, we are going to make it this type of model. Okay. Example, suppose I say about the curvature. Suppose I take example of a circle. What is the arc length of a circle? The arc length S we are going to say R into theta. S equals to R into theta. This is arc length for a circle. This is arc length. S equals to R into theta. Now, coordinates. How we are going to make a coordinates? Polar coordinates. If suppose X, R and theta, that is R cos theta, R sin theta. And when we say theta is S equals to R theta, we are going to make it theta as S by R. So R is cos S by R. Similarly, Y, when we say R sin theta, this is sin S by R. Now, when I make a parametric parameterization of arc, that is AS, that is combination of X and Y with respect to S, that is here XS, YS. Now we are going to change into R cos S by R sin S by R. So this is the arc length, that is AS. Now we have put it in the form R cos S by R sin S by R. Now, after this one, we are going for the tangent. What is tangent? Tangent is A dash S. When you differentiate this A with respect to S, we get it minus sin S by R, and this R will be cancelled because S by R with respect to S by R, you are going to differentiate with respect to S, so it is 1 by R, it will be cancelled, And here also same thing, sign differentiation is cos, and this r will be cancelled with this r. So this is tangent. Now curvature. So when we come to the curvature, so if you see the path, if you see the flow, arc, then coordinate, then tangent, then curvature. Now a double dash s is again differentiation of a dash s with respect to s. Then again we will get minus cos s by r minus sin s by r, and this we are going to say minus 1 by r square as. It means a double dash, if you see the amplitude or magnitude of a double dash s, it is 1 by r. It is 1 by r. Why? We have seen this all things. So arc length, whatever is given, we are going to put it in this form. Then we are going to form a coordinates. Then we are going to see the tangent. Then we are going to see the curvature. Now, see here, this is the tangent. At this point, this is tangent. This is tangent a dash s. Now this is arc, yes, and this is a. So see the beauty here. This beauty we are going to use it in the machine to make it further application in the modeling part. Now, definition of curvature. I already told you what is the definition of curvature. Is the amount by which a curve deviates from being a straight line or a surface deviates from being a plane. For curves, the canonical example is that of a circle which has a curvature equal to the reciprocal of its radius. That I already told you now. Now, definition of a curvature, the normal direction n towards the empty side. The normal direction n towards the empty side. It means a double dash s, you can say kappa s or ks, ns, ks is the curvature. Okay, so this is the normal. This is the normal which is going towards the empty side. And if you see a dash s into a dash s is 1. A dash s into a dash s is 1. A double dash s into a dash s is 0. These two from a dash s dot a dash s is 1. And that implies when you go for the double derivative of a and single derivative of a product, that is curvature and a dash product, you will get a 0. Why? Because it is normal to that one. So this is the one part. If you see this any contour type, see this is kappa s or ks is known as a curvature here. So this is a curvature. Corner model and its signatures. What do you mean by the corner model and its signature? Let us see here. What do you mean by the corner model and signature? So when I say corner model suggests that player development needs to be looked at from a technical, physical, psychological, and social point of view. It means corner model means through all the points we have to see in all directions. For example, if suppose I take some football player development needs. Suppose I want to develop one player on the system. So player development needs to be looked at technical. One is technical aspect, physical aspect, psychological aspect, social point of view. And that no corner works in isolation from the others. No corner works in isolation from others. That is the meaning of the corner. So this corner model, so here you see this dots, A, B, C, D. These corners, we are going to say corners, okay? And S is 0 here. Now, if you see arc length in this, Cartesian coordinate in the coordinate system, A to B, C to D, and then again A. A to B, C to D, and then again. It means A to B, B to C, C to D, and then again to A. Now, if you see on the coordinate system, this is the graph for the arc length. This is the graph for the arc length, if it is in this form. If it is in this form, suppose rectangular form, A, B, C, D, then this is the graph for that. This is the graph for that one. And if it is in a circular form, it's a straight line. It's a parallel to x-axis. It's a straight line like this. So this is known as corner model, And the signatures means we can create, nowadays digital signatures have been created by this concept only, this corner model concept only. So the corner model, and we can have it as signatures on that. Gaussian filter and scale space. What do you mean by the Gaussian filter? In electronics and signal processing, a Gaussian filter is a filter whose impulse response is a Gaussian function or an approximation to it, since a true Gaussian response would have infinite impulse response. Once again, what is Gaussian filter? In electronics and signal processing, a Gaussian filter is a filter whose impulse response is a Gaussian function, okay, or an approximation to it. Since a true Gaussian response would have infinite impulse response, therefore filter we are going to use. Okay, filter we are going to use. And what is scale space? Scale space theory is a framework for multi-scale signal representation. Multi-scale signal representation developed by the computer vision, image processing, signal processing communities with complementary motivations from physics, biological visions, and number of things. So that is scale space. Now, if you see the Gaussian filter and scale space, one by one, you please see it. See the for this type of Gaussian filter, this is the graph. For this type of Gaussian filter, this is the graph. And for this type of Gaussian filter, you are going to be. It means this is the original. And from this, it is filtered like this. 1, 2, and 3. For one, this is the graph. For this is the graph. For this one, this is the graph. What does it mean? It means this we are going to see in the application part of electronics and signal processing. And now these days, this military peoples are using in our military sector, in our confidential, when they send a signals from one place to another, they are using this one. So in electronics and signal processing, what you say, to scale the signal representation, the filters and scaling is going on, scale space is going on there one. Okay. Now, curvature scale space description. Suppose I want to speak about the description. See the fish here. This is a fish. Now, this is the description. Now, see, we are going to read about this one in this graph. So this is fish. This is the outer model of this one, and this we are going to study in our simulation. So this is known as curvature. See the curvatures here. These 4 points are the curvature. These are the points curvature. Okay. So these curvature points are going to be, see here in this one, and this is the simulation is going on. Simulation is going on in this one. So curvature scale space description is like this. Okay. And this we are going to use to make it in the machine, how to read a machine, this fish or something, how to recognize this one in the computer world, or in the for the better world to see how and what is what on the system. So if I want to do it on the system, now see this one. This all points are known as the curvature scale. Every point is going. See, this is a curvature, this is a curvature. This everything I am going to simulate in this one. So simulation is going on here to see the part. Okay. This is simulation going on for this type of model. So whenever it is going to move, it is going to have a simulation from down to up. And the total graph can see, we can read about the total graph, and we have a model for that. Now, curvature of surface. I already told you curvature of surface, the Gaussian curvature of a surface at a point is defined as the product of the two normal, principal normal curvatures. as the product of the two principal normal curvatures. It is said to be positive if the principal normal curvature is the same direction, and negative if the curve is opposite directions. Now see here, this is the point on the surface. This is the arc on the surface. Now the normal section on the surface is like this. This is the normal. Okay. Now see, non-normal section is like this. Normal section is like. How to differentiate the normal section and normal section? This is normal section. This is non-normal section. How? Because when you take a normal here, it should be from the midpoint of this one, or it has to divide or to meet the two midpoints of this shape. Here, it is inclined to some angle. The normal is inclined to some angle. So this is non-normal section. Okay. Now, see, this is going to be happen here, this line. Now see, when I say E1, E2, even at some theta angle from the axis, and E2 is having some angle with that one. Okay, now you see here. Okay, so normal section. Okay. Okay. Now, principal curvature for this one is when we say plane, for all directions, kappa or K1. K1, K2 is 0 for all directions when you take a plane. When you take a sphere, all directions, K1 and K2 both are equal and it is less than 0 when it is a sphere. When you take a cylinder, this K1, K2, K1 is less than 0, K2 is equals to 0 in the case of cylinder. When you take an ellipsoid, K1 is less than 0, K2 is less than 0. When you take a hyperboloid, K1 is less than 0, K2 is greater than 0. So these are the conditions when we put a shapes, different shapes, right from the plane, sphere, cylinder, ellipsoid, hyperboloid. So these are the things what we are going to see. So Gaussian curvature and mean curvature, how to calculate? I already told you the curvature means Gaussian curvature. We are going to calculate by the product K1 and K2. So the Gaussian curvature is going to have a product that is K1 into K2, and suppose we say K. And when we say mean curvature is the average of the two, that is K1 plus K2 by 2, and that we call it as H. So when we say Gaussian curvature and mean curvature for all the shapes, just now I have shown you in the previous slide. Here I will show about what about the mean curvature, what about the Gaussian curvature in case of plane, in case of circle, in case of different shapes. So when you say the first shape, K1 is 0, K2 is 0, so K is 0 and H is also 0. When you take a circle, K1 is less than 0. When you take the second shape, you see K1 is less than 0, K2 is less than 0, K is greater than 0. Why? Because when you make a product of two less than zeros, the product is greater than 0. And H is always less than 0. When you take the third one, K1 is less than 0, K2 is equals to 0. Then the K is equals to 0 and H is less than 0. When you take a fourth one, K1 less than 0, K2 less than 0, K is greater than 0 and H is less than 0. When you take the fifth one, K1 less than 0, K2 less than 0, K is less than 0, K1 less than 0, K2 greater than 0, K is less than 0 and depends on the H. So these are the Gaussian curvature and mean curvature value for the different type of shapes. When you go to the parabolic point, K equals to 0 for a parabolic point. If you see here, see this is the parabolic point here. This is the parabolic point. Okay, from here the parabola is going to the start. So K is greater than 0 when it is elliptic point. When it is K is less than 0, when you are going to say hyperbolic point. So when it is a parabolic point, K is 0. When it is a elliptic point, K is greater than 0. When it is a hyperbolic point, K is less than 0. Point means like this, where it is going to change. This is the parabolic point. Suppose it elliptical it is going on, then it is a elliptic point. When suppose it is hyperbolic shape it is going to take, we are going to say it is a hyperbolic point. Klein used the parabolic curves for a peculiar investigation to test his hypothesis that the artistic beauty of a face, when they are doing about the face recognition of a face, was based on certain mathematical relations. He has all the parabolic curves marked out on the Apollo bell width, but the curves did not possess a particular simpler form, nor did they follow any general law that would be discerned. It means knowingly, unknowingly they have got it, but the certain mathematical relations are the base for that one. They have later on known. This is a geography, suppose. When we see the geography, when we use differential geometry on the geography, you see here, for this type of thing, K is 0, H is 0. This is planes. When you go cylinder type of thing, K 0, H not 0. When you go to this one, K greater than 0, H greater than 0. When you go to this one, K greater than 0, H less than 0. When you go to this one, K less than 0. So this type, when we see the curvature, when we study the curvature on this one, so weather reports people, what you are seeing in the news, and when they are going to capture the videos from the live part, at that time, the people, they are doing as curvature. The curvatures are important in that one. They are going to be captured in the camera, and then we are going to put it on the screen to see the people what is going on there. So other feature points and edges. So other feature points and edges are, edges means maxima of the curves. Maxima of the curvature is known as the edges. Zero crossing of Gaussian or mean curvatures, ridges and valleys, umbilic point, principal curvatures are the same. What do you mean by the umbilic point? I will tell you about the umbilic point. What do you mean by the umbilic point here? So when I say umbilic point, in the differential geometry of surfaces, in 3 dimensions, umbilics or umbilical points are points on a surface that are locally spherical. At such points, the normal curvatures in all directions are equal. At such points, the normal curvatures in all directions are equal. Very beautiful concept, this umbilic point. At umbilic point, the normal curvatures in all directions are equal. Hence, both principal curvatures are equal. Both the principal curvatures are equal. And every tangent vector is a principal direction. The name umbilic comes from the Latin umbilicus, that is navel. It's a very beautiful concept, umbilic point. What is that one? A point where the normal curvatures in all directions are equal. First point. And what happens if this type of thing is going on? Hence, both principal curvatures are equal, and every tangent vector is a principal direction. Every tangent vector works as a principal direction. Now, you can ask that how this all things we can use in the machine learning. So when I want to make a tangent vector as a principal direction, all vectors to work in a principal direction, I will use this umbilic point. I can give a command to the machine to pick up the umbilic point such that every tangent vector is a principal direction. These points can simply be represented by their coordinates. These points can simply be represented by their coordinates. A local description of a curve is given by the point coordinates and its associated tangent or normal. So a local description of a surface patch is given by the point coordinates and is associated normal. Here, however, we do not know in advance what type of entity, that is point, curve, surface, a token may belong to. Furthermore, because features may overlap, a location may actually correspond to multiple feature type of the same type. At the same time, when the multiple features are there, the system has to catch, the system had to take and to push on this one. So what is going on there? The points can simply be represented by their coordinates. It means oblique points. It is going to be simply represented by their coordinates. And the beauty of the oblique points is the curvatures in all directions are equal. Both principal curvatures are equal, and every tangent vector is a principal direction. So when we need every vector should be a principal direction, we use this oblique point. So this is about the oblique point. Principal curvatures are the same. That's why it is written principal curvatures are the same. What does it mean? Principal curvatures are equal, and every tangent vector is a principal direction. Okay. Now, lines of curvature. If you see the lines of curvature, you see the diagram right side. Principal direction, which gives the maximum and the minimal normal curvature, is known as principal directions, which gives the maximum and the minimal normal curvature. Principal direction. See the right side curve. What you can say here. This diagram, if you see, and curves along principal diagram. Curves along principal directions. See, these are the curves. This is one. This is principal direction. PD. Principal direction. Principal direction. Principal direction. It's going on like that. Now these are the curves. See, this is the shape. Minimal, maximal. So these are. This is the thing going on, and this is the part. And now these days, this not only machine learning, the data science is in the top in the world. Now this differential geometry plays a very important role now on the data science also. See, these all are data, and you are going to see this one. So this lines of curvatures, how we are going to make it and how we are going to combine and consolidate it. So see the lines, for example, see the lines of curvature. These are the lines of curvature, and you seeing these two. I can make it from this one. See these two jugs make from this one. See, so these are the things how. So the manufacturing part, the industry part, all are using now the machine learning. The human interference is less, and the machine, the smart knowledge is more. Now in all industry, they are using only this type of concepts to make it the products. So see, these are the lines of curvatures and these are the curves. No human only giving the input. Now the output is like this. So it means the system had studied about, or system have a knowledge about the curvature and all the things, how it should be. So curvature, primal sketches along lines of curvature. Now see, suppose I want to make a human face, which you know as a mask like that, or some plastic surgery type of thing, or something to make it a robo, and the robo human face, human robo face is something similar to some other face. So for that also, if you see curvature primal sketches, we are going to have it. This is the curvature primal sketches along lines of curvature. Only along lines of curvatures can give the shape of that one. See this one. Okay. And what are the formulas for this one? Very simple formulas, what we have studied in our degree and our PG part. So surface x can be given as xy, and it is dependent on u and v. That is two u and v are the dependent variables, and x, y, z are 3-dimensional, because when we see about the 3-dimension like this, and the total thing we are going to put it into xy, then I say x, y, z is going to convert from uv to xy. So the total surface x, now we are going to put it in xyz as x and y. So this is xu, this is xv, and this is normal. So surface normal n can be given by the cross product of u and v, by the modulus of that one, or the what you say scalar part of x cross u. So mod of x cross u. The fundamental form, the first fundamental form, it is known as, I think all of you have studied in your degree or PG first year. The first fundamental form is known as E of G. E is xu dot xu, f is xu dot xv, g is xv dot xv. And the second fundamental says E of G, small e of G, it is normal n dot xuv, n dot xuu is E, xuv is F, xvu is known as G. So these are the things what we are going to see in the formula. Okay, so these are the important formulas what we are going to see in this regard. So first fundamental form and second fundamental form is important here. Now, important formula 2. Hello. So this is important formula 2. What is important formula 2? Arc length, now you see here, this is from 0 to S, integration from 0 to S, E square 2F du dv g dv. So E du square 2F dot du dv g dv square. This is known as how to calculate the arc length, and the area is going to be calculated. When we say length, it's a single integral. When we say area, it is a double integral. When we say volume, it is a triple integral. So area we are going to say on the curve, double integral square root of Eg minus x square. Now Gaussian curvature, if you see Eg minus f square by capital Eg minus f square, this is the formula to calculate the Gaussian curvature. And mean curvature is given by 1 by 2 Eg minus 2f f plus g and Eg minus f square. So these are the important formulas when we calculate the curvature, when we see the Gaussian curvature, when we see the mean curvature. Okay. Now example, if you see the example here, this is the shape, xyz is 3D, and this I am going to give a phi angle, and this I am going to give a theta angle. So x theta phi, we can write it like this, coordinates with respect to theta and phi. And when we convert into r theta phi, r sin theta cos phi, all of you know what is the conversion. That is r sin theta cos phi, r sin theta sin phi, r cos theta. This is the polar representation of any r. Now x theta is r cos theta, r cos phi, r cos theta, r sin phi minus r sin phi, because it depends on the direction. So x theta, x phi, E, F, G can be taken from this diagram. If you see carefully, this all calculation has been done from this one and the previous formula. So this, after getting all this x, E, F, G, we are going to calculate n. N is going to be calculated by x cross x with respect to theta and phi, and the same scalar part divided by the scalar part. So this we are going to put it in the matrix form ijk, and we are going to calculate. So n we have calculated as sin theta cos phi, sin theta sin phi, cos theta. Now we are going for theta theta, theta phi, phi phi, small EFG. Capital EFG has been done previously. Now small EFG we are going to see here. After this calculation, we are going to calculate the arc length. Arc length depends on the formula which we have just now, I have shown you on the slide. The integral square root of E d theta square 2f d theta d phi g d phi square. And this is the diagram for this one, what we have done. And the area is calculated by Eg minus x square. So this is the calculation of the arc length and the area. And all areas you can calculate by the formula r square 0 to pi sin theta d theta, 0 to 2 pi d phi, because double integral is there. One integral is with respect to sin theta d theta, and one integral is with respect to d phi. And this is the 360 rotation, 0 to 2 pi. Okay. So GC and MC can be calculated, Eg minus Gaussian curvature and mean curvature can be calculated with the formula what I have shown you on the screen. That is Eg minus h square by capital Eg minus h square. Like this, we can calculate the Gaussian curvature and the mean curvature, and see this is the diagram for the two things. Okay. So estimate normal and curvatures of polygon mesh model. So if you see the polygon mesh model, normal, so weighted average of normals of the adjacent faces, fit plane, and curvature, fit algebraic surface, fit circles, kappa is needed here. kappa equal to kappa and cos phi. Curvature tensor is here. So curvature tensor, I will show you. This is the diagram for tensor decomposition. So what is going on here for the tensor decomposition? You see, to capture first order differential geometry information and its singularities, a second order symmetric tensor is used. Okay, it captures both the orientation information and its confidence or silence. Such a tensor can be visualized as an ellipse in 2D or an ellipsoid in 3D. Intuitively, the shape of the tensor defines the type of information captured: point, curve, surface, element, and its size represents the silence. By perceptual silence, we mean the perceived importance of structures such as surfaces, curves, junctions, regions. For instance, in 2D, a very silent curve element is represented. What is on the screen? You please see that one. Curve element is represented by a thin ellipse whose major axis represents the estimated tangent direction and whose length reflects the silency of the estimation. If you see the diagram, everything I am going to explain. In 3D, a point on a smooth surface is represented by a tensor in the shape of an elongated ellipsoid, that is stick tensor, and its major axis along the surface norm. A junction of two surfaces, a curve, is represented by a tensor in the shape of circular disc, that is plate tensor, which is perpendicular to the curve's tangent. Alternatively, the plate can be thought of as spanning the 2D subspace defined by the two surface normals in the case of the surface junction. Finally, an isolated point or a junction of curves have no orientation preference and it represented by a tensor in the shape of a sphere, that is ball tensor. This is ball tensor. What you are seeing, this diagram is a ball tensor. Any second order symmetric tensor, therefore, can be decomposed in the basis tensors. What is the mean of basis tensors? Stick, plate, and ball in the 3D case. The tensorial representation allows for a unified treatment of in layer of smooth structures, depth and orientation, discontinuities, and noise before any hard discussions or decisions are made for the role of each point. So here, by this, we can we can stop noise disturbance or orientation disturbance or depth, and everything can be managed here. So this property is extremely useful in perceptual grouping when the role of a point cannot be determined accurately from the initial data. Instead, the tensor represents the likelihood of all potential roles the point can play simultaneously. Very beautiful orientation tensor voting is here. And what do we mean by the tensor voting? The input tokens are first encoded as tensors. In 3D, a point is encoded as a 3D ball. A curve element is enclosed as a 3D plate. A surface element is encoded as a 3D stick. If you see here, this is plate tensor, this is plate tensor, this is stick tensor, this is ball tensor. Okay, the input tokens are first encoded as tensors. In 3D, a point is encoded as a 3D ball. See, this is 3D ball tensor. A curve element is enclosed as a 3D plate tensor. A surface element is encoded as a 3D stick tensor. This one. Okay. These initially tensors communicate with each other in order to derive the most preferred orientation information or refining the initial orientation if given. For each of the input tokens refinement or pairs tensor vote and extrapolate. Interpolation and extrapolation you have seen. So extrapolate the inferred information at every location in the domain for the purpose of coherent features extraction. So dense extrapolation or dense tensor vote it is known as. Each token is first decomposed into the basic tensor and then broadcast it information. So broadcasting, for example, what we people are doing, what the Gates people are doing now, that they have put it as Zoom link and they are pushing into YouTube, right? So each token is first decomposed into the basis tensor and then broadcast its information. So we can do a magnificent output when we use this part to the machine. Okay, a voting field for each basic component is used to look up the orientation and magnitude of the vote cast. All voting fields are based on the fundamental 2D stick voting kernel. Kernel has to be created. I will show you. Estimate normal using tensor voting. The voting is the first part. See, this is point, what I have told you. And this is the next point. This is the normal. This is going to be a arc. This is going to be inside, that is O to P. Okay. Now, estimate curvature using tensor voting. This is the shape. Estimating tensor curvature tensor is given by the formula. If you see, this is the curvature. You see the diagram here. This is going on towards outside. Okay. Now, radius hit is there, is this one. Now see, these are the points. See, this is the radius hit area. Okay, if you see like this. Now see, I am showing you, this is radius hit from there to there. Okay, so, and what is the summary? Curvature of curve, curvature of surface, that is Gaussian curvature and mean curvature we have seen. And if you see the extended Gaussian images, so Gauss map, extended Gauss image, and application of Egi. So I will see here, Gauss map is a map. Gaussian mapping, we are going from, see, these 2 points, these 2 are normals with respective points. This Gauss map from this to circle. This is 1 dimension. From when you say this one to this one, this is 2D dimension, 2-dimensional this. Now, here S is a subset of R cube surface with an orientation N, and the mapping is used. We are going to create S square XYZ like this, and then map, we are going to make it S to S square, and this map is known as a Gaussian map. So, like this, we are going to make a Gaussian map, and we are extending this Gaussian image. So, what is this one? Egi, extended Gaussian image. Distribution of normals represented in the spherical coordinates. A weight is expressed the area of the surface having the given normal. See this one, and this normals we are going to analyze like this. Okay. Characteristics of extended Gaussian image. So EGI is the necessary and sufficient condition for the congruence of 2 convex polyhedral. Ratio between the area on the Gauss surface, the Gauss pair, and the area on the object is equal to Gaussian curvature. Gauss pair, Gaussian curvature. So EGI mass on the surface is the inverse of Gaussian curvature. Mass center of EGI is at the origin of the sphere. An object rotates, then EGI of the object also rotates. However, both rotations are same. See, when the object is going to rotate, it is captured by the machine and it is pushing towards the world. At that time, EGI of the object rotates means if the object rotates, EGI of the object rotates and rotates in the same direction. Okay. So relationship between EGI and Gaussian curvature. So object is here. This is object. This is K. Limit delta O tends to 0, delta S by delta. When you go for the limitation, when you go for the take a limit as small as, see here, Gaussian surface. Okay. When you go this one large, at that time we are going to say the ratio is small and this is small. When you go this one small, K is large. Here object, K small, K large, this is large. Okay. This is the relation. So Gaussian curvature and EGI maps. If you see the Gaussian curvature and EGI maps, it is like this. Okay, it is going to map like this. This is the mapping. So these two exist on the tangential plane of X. We can represent them by the linear combination, and this linear combination we can show like this. So these are all the presentation, how we can put it a dot product for all the things, and we can put it in the matrix form, and how to calculate EGI mass and EGI matrix. So implementation of EGI for unit sphere, tessellation of the unit sphere, all cells should have the same area, have the same shape, occur in a regular pattern. For example, if you see the football, this is polyhedron, geodesic dome based on a polyhedron. This is regular polyhedron. Semi-regular geodesic dome. This is semi-regular geodesic dome. Example of EGI. If you see these two, this is side view, this is top view, down. This is side view. These two are the side view, and this is the top view. This is cylinder, this is ellipsoid. Determination of attitude using EGI. So view directions and go to this table, and then EGI table has to form, and then we can decide what is this surface. So determination of attitude using EGI. The complex EGI, it means the complex extended Gaussian is also there. What is that complex? So weights are complex weight, and we are going to encode 3D into complex weight, and again the tokens can be generated for this one. Okay. The complex EGI looks like this. See this part. So previously it was not like this. This is the part included when you have a complex part. This is cube. Each complex EGI of a cube is like this, and this is a Gauss mapping. You see the example of this one, what is on the screen. If you see this one, this is like this. If you see this one, this is like this. See. So bin picking system based on EGI. Photometric stereo, segmentation, region selection, photometric stereo, EGI generation, EGI matching, and grass planting. So photometric stereo, needle map, isolated regions, then target regions, precise needle map, EGI, and object attitude. So this is the flow for this one. So calibration is lookup table for photometric stereos. Hand-eye calibration is like this. Okay. Photometric stereo setups are like this. Bin picking system is like this. And what we have seen today, the total summary is we have seen about the Gauss map, extended Gaussian image, characteristics of EGI, congruence of two convex polyhedron, EGI, implementation of EGI, tessellation of the unit sphere, complex EGI, bin picking system, and horn PPT. So these are the things what we have seen today. And this is my talk today about the differential geometry. And I request the organizers, if any participant want to interact, they can please interact with me in this subject, please. Hello.
Sir.
Yeah, please.
Sir, no participants are there, sir.
No
to ask
participants.
any question. No, to ask a query, sir.
See in the chat box. See in the chat box.
Sir, seeing, sir. Just a minute, sir, please.
Yeah.
Sir?
Yeah, please.
No questions from participants, sir.
Okay, fine. So this was my talk. So anything you can, anything they can put it a mail to me. It's not an issue.
Okay, sir. Okay, sir.
So I will stop my sharing and then.
Thank you so much, sir.
Yeah, please. Okay, fine. Thank you. Thank you for giving me this opportunity to speak on differential geometry and the application to machine learning.
Thank you so much, sir. On behalf of H&S department, today I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Professor E. Keshava Reddy, sir, accepting our request and for giving such a wonderful presentation on a differential geometry for machine learning and making event meaningful and interesting. Thank you very much, sir. I would like to thank our chief guest, Professor R. Bhuvana Vijaya Madam, for accepting our request to be a chief guest for this FDP and sparing her precious time on this event. I would like to express our profound gratitude to our principal, sir, Dr. D. Venkatesh, sir, for his constant supporting and encouragement throughout the program. Thank you so much, sir. Sir, excuse me, sir. Sir,
Yeah.
one query from participant, sir.
Yeah, please.
Which
Yes, please.
software useful for mathematics? From Ahmad, sir.
Which software is?
Which software is useful for mathematics?
No, there are number of softwares, Mathematica, what you say, SSP, and number of softwares, MATLAB, Matrix, number of softwares are there. It depends on the application on which we have to use it. And rather than the software, we have to first develop the algorithm, because software is only for the existing thing. If we want to do something for the new or something to apply on the new, we have to write an algorithm. Then algorithm can be put it in the form of software or coding. So algorithm, you have to put it first, and then you can go for the coding, and then you can use that software for a particular type of thing. So this here, you can use any software. For example, you can use Mathematica here. MATLAB can be used frequently. You can use Origin for report generation. You can use what you say, statistical softwares are there, SSP. So that type of thing we can use it here. But for a particular program, when we have a problem, for a particular problem, we have to write an algorithm. And that algorithm, we can take some computer science people help to make it a code, that is coding. And then that coding can come into a software. It's not we can say it's a particular software. So there are a number of softwares there to have it, all these things.
Thank you for your answer, sir. I would like to extend my heartfelt thanks to our beloved correspondent, Madam Srimati V.K. Padmavathamma Garu, for her encouraging words at the time of inaugural session. Thank you, Madam. I would like to express my gratitude to our Managing Director, Shri G. Raghunath Reddy, sir. Thank you so much for supporting us, guiding us in a right way, sir. Thank you so much, sir. And next, I would like to thank our Director, Madam Srimati Srivani Madam Garu, who has initiated to us this program and her continuous support right from its inception. Thank you so much, ma'am. My heartfelt thanks to our convener and the HOD of H&S department, Dr. G. Haripriya ma'am, and her entire team, Dr. Vijayalakshmi ma'am, T. Suman Gopinath ma'am, Shivaya sir, and Angeline ma'am for their continuous support in making first day of this FTP successful. A big thanks to Noor Ahmad sir and PT Nageshwar sir by providing technical support. Thank you so much, sir. Finally, at the end of the session, I would like to thank all the participants of this FTP for their glorious presence. Thank you one and all. And my special thanks to Professor E. Keshava Reddy, sir. Sir, thank you so much for sparing the time with us, sir. Thanks a lot, sir.
Thank you very much. Yeah. Shall I leave now?
Okay, sir. Thank you, sir.
Yeah, please. Thank you. Thank you very much.
Dear participants, please fill the feedback form we provided in chat box. Dear participants, please fill the feedback link